to this video tutorial on the very basics of ellipses. There's a bit more to ellipses than what's covered in this tutorial, but we'll start with the very basics, and it follows on from our previous tutorial on circles. And we'll actually start with a unit circle. So what was familiar to us from last lesson and here at methods as well was a unit circle where we have a radius of 1. Pythagoras starts us off with x squared plus y squared equals to 1. Our circle is drawn there, centre at the origin, points P, X, Y, what we looked at last time. We spoke about not considering other transformations other than the translations when we looked at the circle work. We're now going to think about what happens if we were to apply dilation factors. So remember, dilation factors are a multiplying factor. They stretch our particular graph from whichever axis or in which direction we'd like to actually stretch our graph. So they actually change the shape of the graph. We can apply dilations here of a factor, so again a multiplying factor, a factor of a from the y-axis. So remember, if you want to head in this direction here from the y-axis, you're actually stretching it by a factor in the x direction or from the y-axis. So just repeating those terms, it's in the x direction or from the y-axis. And that's going to be our terminology we use pretty consistently across both specialist and math methods. Likewise, we can apply a dilation factor of b from the x-axis. Okay, so from the x-axis, we can stretch our graph in the y direction. Okay, so from the x-axis, we're actually stretching our graph that direction. And you can think about what that happens. We're no longer going to get a circle if our dilation factors are different. So if a and b are the same factor, we'll still end up with a circle, be it a smaller circle or a larger circle, depending on our numerical values for a and b. But if we choose different values for a and b, we will actually change the geometric properties of that shape, so it's no longer a circle. In fact, what we'll create is what the essence of this tutorial is about. We'll create an ellipse. So our transformed equation, and we'll talk more about these transformations and how they apply as you go through your methods course, but we're looking at a transformation of x over a before we square it and y over b before we square it as well. Okay, so at this stage we'll accept that. We may have seen, some of you may have seen this in your methods, but at this stage we'll just think about why that transformation occurs where it does. Expanding those brackets there, you'll look at x squared over a squared plus, it's important to pick up the plus sign, y squared over b squared equals to 1. So one of the key differences here from the circle work is we're always going to end up with equals 1 on the right hand side. We're not looking at some sort of radius squared factor on the right hand side of these equations. So looking at some of the properties of these ellipses, as I said, it depends on the size of our dilation factor A and our dilation factor B. We can get two general shapes. One is a factor of A bigger than B, so we've stretched it more in this direction. So from the y-axis or in the x direction has been stretched more than in this direction here. In fact, we may have compressed it in this direction if B was less than 1. Or vice versa in this situation here, B is larger than A or A is smaller than B conversely, and you've got some sort of squashing effect in this direction here. Okay, the terminology is exactly the same in terms of the points. A dash, that's a reflection across the axis in this case, B dash, and you're going to get coordinates based on those values of A and B that you choose. So our x-intercepts here are going to be A0 and minus A0. Likewise over here, just depending on the scale of the drawing, and 0B and 0 minus B will be our y-intercepts as well. Same sort of techniques. If you want to find intercepts, let x equal 0, we'll find a y-intercept, let y equal 0, find an x-intercept. Some of the terminology here, we're going to talk about a major axis being the longer direction and a minor axis being the smaller of the two dimensions. So these situations unfold where A is greater than B, and conversely when A is less than B, we'll switch around the terminology for minor and major axes. Now we can go back to our work on translations from circles, and we'll look at a vertical and horizontal shift. So xy, any point xy, including the centre, will be shifted plus h units in the x direction and plus k units in the y direction. Okay, so there are vertical and horizontal shifts. Putting this all together, it'll start to look like that circle form we looked at before, x minus h squared over a squared and y minus k. So opposite signs. Null factor law, so to speak. We've got plus h there, but we've actually moved it the opposite direction, minus h. And likewise for our vertical translation, plus k, you'll see there's minus k within the brackets there. Again, reinforcing we've still got equals to 1 on the right hand side, even after these translations. New centre of our ellipse will be the value h and k. There are some other key properties of ellipses. We can look at defining ellipses in various ways. You may come across terms like focus and foci that revolve around points within the circle. At this stage in this introductory work, we won't look at the focus or the foci of those particular ellipses. The actual example, so putting this into practice in terms of the skill set that you're going to require from this particular part of the course, we're looking at very similar work to what we did with circles. So this particular form, we have it all expanded. Okay, we're going to have to group our terms together and complete the square where appropriate. I've changed the example slightly from the first one in terms of not both terms need completing. Our x term will need completing, but our y term is already a standalone term. And we've got some sort of non-monic quadratic to look at here in terms of our x squared. So the technique there is exactly the same. We're going to group our x's and y's together. I've done that in colour-coded that in blue and red for you. Take out a common factor of 3, so 3 lots of x squared plus 8, which lets us complete the square inside the bracket there. As I said before, the y doesn't need anything doing with it, so that's just going to maintain its form through there. And our coefficient, our constant, our 36 is going to be transferred to the right-hand side, similar to what we did with circles to set up the circle work. Okay, 3 lots of completing the square inside the bracket. We're going to halve that middle term and take away its square. I've sort of accelerated through the process there. Then expanding the brackets back out. You may use two round brackets. I've used the parentheses here. 3 lots of that whole term important. You keep it in brackets because we're going to have to expand not just the 3 lots of x plus 4, but the 3 lots of 16 as well to get minus 48. Okay, so once you've got that, you've got it back in this form, 3 lots of, but you've got this negative 48 that needs transferring across to the right-hand side of the equation. So 3x plus 4 squared plus y squared equals to some sort of numerical value on the right-hand side. Now it's starting to look like this particular form here, in that we've got our horizontal and vertical translations outlined, but we still need to adjust for these dilation factors. So remember, we don't want anything other than 1 on the right-hand side, so we're going to have to divide everything through by 12. So the left-hand side becomes 3 over 12 x plus some particular value, and our y squared on 12. Now this enables us to get both the centre of the circle and pick up any dilation factors of a and b in this particular form here. So we're looking at x plus 4 squared on 4, and that'll be our a squared term, and y squared on b squared. So b squared is going to be 12 equals to 1. From that information, I encourage you to write down what our key points are going to be. Our new centre is minus 4, 0 for the x, and we're going to look at 0 from the y coordinate there. Okay, we've got no shift up and down the axes. From here, we've got to pick up our values. B squared is 4, so B will be, A squared is 4, so A will be 2. B squared is 12, so B will be root 12 or 2 root 3. Remember to simplify your surds where you can. So that'll give us the basic properties. That's enough to sketch the graph again. Like the circles, let's try and keep the scale appropriately. Then we'll be able to pick up from our sketch whether we have intercepts. But algebraic techniques again to find intercepts, as I talked about before. Okay, so we'll be picking this up in class during the week. I'd ask you to finish that particular example, and as we've always said, change some of the numbers here. Okay, no need to use the same example I have. Change some of the numbers and see if you can get an appropriate solution following that technique. Thank you.